Hi everyone. At this point in time, I just really wanted to make this recording to ensure that everyone has the essentials of what we need to know of what we spoke about in the last week. So I think at this point in time, we have had many conversations and many demonstrations and many videos depicting the idea that liquids, water molecules or other liquids exist in something that we call the liquid phase, and the molecules are close to each other because there's a certain level of attraction between the molecules. There are intermolecular forces keeping these molecules close together. So, with that being said, we also spoke about the fact that the molecules are not just sitting there and not moving, but rather they have kinetic energy, and as a result, these molecules are moving around. But we've also established the idea that the molecules are moving at different rates. So, although you can stick a thermometer into a liquid and look and see what the temperature is, that temperature and that rate of movement is not the same for each and every molecule, but instead, temperature is the measure of the average kinetic energy. So, some may be moving very, very quickly and have a high amount of kinetic energy, and some will have a lower amount of kinetic energy. So if you come down here, this graph, which we talked about twice now, is called the Boltzmann distribution graph. And what it does is it helps to show you that there's a particular point at which these molecules have enough kinetic energy. So you can see it says it over here. The molecules that have evaporated do not have enough kinetic energy to overcome the intermolecular attractions and remain as a liquid. But over here, we're looking at the point where these molecules under here that are shaded in green, they actually do have enough energy to break free of the attractive forces. So those are the molecules that we say are able to evaporate. Those are the molecules that escape the liquid, and all of this is able to occur because the molecules are moving. And while they're moving, there are times when they collide with one another. And if you take the liquid and you increase the overall kinetic energy, you're going to have even more of the molecules moving at a faster rate. So I'm going to click on this animation because it's going to show you that you have the molecules having a certain average kinetic energy. And as the overall average kinetic energy increases, you have more of the molecules reaching and meeting that energy level needed to escape. So now, as kinetic energy increases, you have more molecules that are able to evaporate. So now you have increased the number of molecules leaving the liquid phase and going into the gas phase. So we're back to the slide, and the conversation I think that you need to make sure you know is that vapor pressure, the definition of vapor pressure is something that we were really able to observe. It's the force due to the collisions of a gas molecule escaping from the gas phase. Think about if you've ever boiled a pot of water on the stove and it's had a cover on it. Well, if it's vigorously boiling, all of a sudden you hear the top of that pot like clanking around. What's pushing the top of that pot up? What is forcing the top of that pot to be moving? Well, it's these gas molecules. They have escaped the liquid phase, and now they're onward and upward. They're moving. They're going every which way, and they're smashing into the top of that pot. They have overcome the attractive forces, and when they escape, they're creating what we call vapor pressure. So again, just before, we definitely established that as temperature increases, more molecules reach this point of having enough energy to evaporate. So you can say with confidence that an increase in temperature is directly proportional to an increase in vapor pressure. So I'd like to also show you this animation.
Molecules of a liquid have a range of kinetic energies. Some have enough energy to overcome intermolecular forces. If these high-energy molecules are at the surface of the liquid, they can escape into the gas phase. This is an endothermic process.
Okay, I'd like to get to the next slide, and this is going to be something that shows you what it looks like for these molecules, the entire water molecule, to break free from the other water molecule. Now remember, the water molecules are attracting each other through a type of intermolecular force. There's an attraction between the molecules. At no point in time are we suggesting that the hydrogen and the oxygens are separating from one another. This is not a chemical change. This is a physical change. Hold on one moment. Okay, so let's play this video and see what happens. You're looking at molecules. They're in the liquid phase, so they're loosely arranged. They're next to one another. There is an attraction. Oh, wait, look, some are leaving. Some of the molecules are breaking free. Some of the molecules have high enough kinetic energy to break free. Oh, and then some return. So this is the point where some are evaporating, and some of the molecules also are condensing and returning back to the liquid form. So this is another way for you to visualize and see what's occurring when we look at these molecules and talk about evaporation and the kinetic energy required for them to evaporate and the vapor pressure above the surface of the liquid. So because of condensation occurring at the same time as evaporation, if this were in a closed system, you would know that you've reached equilibrium, because the amount of molecules that are leaving and evaporating is the same as the amount of molecules that are returning to the liquid phase and condensing. Let's watch this animation.
In a closed container, molecules move back and forth between the liquid and gas phases. If the rates of crossover are equivalent, the overall amount of substance in each phase remains constant. The system is said to be in a state of dynamic equilibrium.
So we've been spending our time talking about liquids, and that the kinetic energy of the molecules within the liquids allows them to break free from the liquid phase and evaporate. Let's look at the temperatures here for water and look to see what's going on next to the water. So vapor pressure is going to be a measure of the amount of molecules that have escaped. So they're moving up out of the liquid and pushing upward. So as we look, we see at 0 degrees there's 0.611 kilopascals. And as temperature goes up, so 5, 10, we broke into the 1 for pressure. Then when we go to 30 degrees, it's up to 4 kilopascals. When we go to 50 degrees, it's up to 12 kilopascals. 60, 19, 70 degrees Celsius, it's up to 31 kilopascals. Let's check out 100. Oh, look at what we see, 101.32 kilopascals. Something that we discussed in class, that there is this normal pressure. So the pressure pushing up out of this liquid at 100 degrees is 101 kilopascals. Hold on to that thought for a minute. Remember that, please. So let's remember the demo we did in class where I stuck my finger in 3 liquids, in water, in the propanone, and in the alcohol. And what I did was I was showing you that as I took these liquids and I spread them out across the table, that one of them evaporated, looked like rather quickly, almost instantaneously, we'll say. The other one took a little longer, and the third significantly longer. And if you remember, it was the propanone that evaporated right away. It was the alcohol that evaporated second, and then the water that took the longest. So I'd like to go to Table H and look at the rate of evaporation and talk about intermolecular forces and vapor pressure and boiling points and move along that way. So let's take a minute and look at Table H. So So as we look at Table H, we can ask ourselves a few questions and make a few comments here. So we know that the propanone evaporated the fastest. So without even really reading anything off of Table H, we can talk about some concepts here. So we know that liquids are made of molecules, and we know that in order for the liquid molecules to leave the liquid phase and go into the gaseous phase, they have to break their intermolecular forces. So if you were to look at the propanone, the ethanol, and the water, I think we can say with confidence that at this point in time, the propanone had weak intermolecular forces because right away those molecules were able to break free and get out. So if that's the case, if they break free right away, then we know that there's a lot of the gas molecules existing above the liquid, so that means it's going to have a high vapor pressure. And if we look and we compare, if we know about the intermolecular forces, and then we ask ourselves about the boiling points, that's where this table is very helpful. So if we think propanone has weak intermolecular forces and high vapor pressure, then, and we pick a atmospheric pressure, or we pick a vapor pressure of 101.3, then we have a situation where we can see and we can say that the propanone at 55 degrees matches the atmospheric pressure. The vapor pressure of propanone is 101.3 at 55 degrees Celsius. But the ethanol, it requires much, much more energy to get the vapor pressure up to 101.3. It's at about 80 degrees Celsius that the ethanol are able to break the intermolecular forces. The ethanol molecules are able to break the intermolecular forces. And then the water does not create a vapor pressure until it reaches 100 degrees. And then the ethanoic acid, this is up at around 118 degrees. So each of these liquids has a different temperature at which they have a vapor pressure of 101.3. So we're noticing that the propanone was able to evaporate first. It's the steepest slope. It reaches this 101.3 kilopascals of pressure at the lowest temperature. It reaches it the fastest. So we can say that it has, again, weak intermolecular forces, a high vapor pressure, and a low boiling point, because we need to spend a little time talking. So before we go and talk about boiling points, let's just definitely reinforce something we talked about in class. We spent some time talking about liquids, and I had a few students that were able to give me a phenomenal answer when I asked the question, when do liquids evaporate? And one of my students, in a very funny little voice, said, all day, every day. And I don't know if I just got that right, but the point is that evaporation, water molecules or liquid molecules being able to escape the liquid and become a gas, is happening all the time. But when we start to talk about this idea of boiling, that is when we talk about a maximum rate of evaporation. And let's look at it, what it takes for that to occur. So right before we move on to look at boiling, we definitely need to establish that the temperature at which a liquid vapor the temperature at which liquid's vapor pressure equals atmospheric pressure is called the normal boiling point. So that's been established as the standard pressure, and we will continue to talk about this. Now let's take a look at this next slide, because it helps us. Hold on one second. Okay, so this next slide helps us to visualize what's going on. So we said evaporation is occurring all the time. So here we have some of the molecules having enough energy to get out of the liquid form, but we also have this idea of this atmospheric pressure. There are molecules surrounding us in the air, and those molecules have mass, and as a result, they're being pulled down to the earth and exerting a force on us. Okay? So the force that's coming down we call atmospheric pressure, and it's being represented right here with these yellow arrows. And if you notice, the vapor pressure at this point in time is not matching the atmospheric pressure that's coming down. But over here, we have a higher temperature. That means we have more molecules overcoming the intermolecular forces, more molecules leaving the liquid phase and going into the gaseous phase. And now we have the molecules that are leaving, meeting, and matching the molecules that are pushing down. At this point in time, we have reached the maximum rate of evaporation, which is what we call boiling. In addition to that, we spent some time looking at what occurs if you change this pressure. If you move away from the normal pressure, the normal boiling point, the standard point that's been established and that was made for comparison, when we change that pressure, we see things occurring and happening. So let's go back to Table H. So we can see graphically from Table H, something that we know and we've talked about regularly is water. So make sure you're careful when you're using Table H. So put your finger or highlight or your pen on the water line, because we're going to spend some time talking about water right now. And water, when it's at that standard or that normal pressure point that we've decided the normal boiling point is, it's on this dotted line on Table H. And when I run my finger down to the temperature, I see it's 100 degrees. So we know that 100 degrees is when the vapor pressure pushing up, the 101.3 kilopascals, matches the atmospheric pressure. So this is where boiling occurs. But what happens if we increase the pressure? All of a sudden the pressure, instead of being 101.3 kilopascals, it goes up to 110 to 120. So if we're at 120 kilopascals and we come across, and again we have to hit that water line, and then we go down and look at the temperature, well, now water is matching the atmospheric pressure at a higher temperature. It takes more energy to get those molecules to have the ability to escape the water and create the vapor pressure and match the atmospheric pressure. But what happens conversely if we lower the pressure? So if we put the pressure down to 30 kilopascals, then all of a sudden we hit the water line and we're able to see that water will boil at 70 degrees Celsius. So anywhere on this line, the vapor pressure is matching the atmospheric pressure, and as a result, boiling is occurring this entire time on this line. So you can find that water, and any liquid for that matter, can boil at any temperature, but it definitely depends on what that pressure is. Okay, so let's stop there. We've definitely done a good job of establishing that liquids require a certain amount of energy to break free and become a gas, and it's the gas that exerts a pressure, and if that vapor pressure that exists above the gas is able to match the atmospheric pressure, well, then we have boiling occurring. And as you can hear, my dog is continuing to complain, so I'll be done for now. Good night.